Now we are discussing the what is the motivation for MobileNet. Until now we have discussed about LeNet 5, AlexNet, and VGG16, ResNet, and also we have covered InceptionNet. Now we are discussing about MobileNet. Before discussing the MobileNet, let us discuss about motivation for the MobileNet. What is the requirement for this MobileNet, even though there are several other networks are existing? The main motto behind the motivation for the MobileNet is low computational cost. As the name suggests, mobile, this network, even it can work with the CPU of a mobile. That's why they have named it as a MobileNet. It is very useful for mobile and embedded vision applications. This paper was published in 2017, and the title is MobileNets, Efficient Convolutional Neural Networks for Mobile Vision Applications. In order to understand the MobileNet, first we will understand what is the difference between normal convolution and depthwise separable convolutions. Now we are discussing about normal convolution. We have considered an input image with size 6 by 6, and this is having 3 channels. So it is 6 by 6 by 3, and we have considered a filter, 3 by 3 filter we have considered, and it is having 3 channels. So it is 3 by 3 by 3, and output is 4 by 4. Because we have considered input size 6 by 6 and filter size 3 by 3, output size is 4 by 4. It is like we are taking an input image n by n and filter f by f, and number of channels NC we are taking. Then the output size will be n plus 2p minus f, where p is the padding, f is the filter size, by s is the stride, plus 1. This we already discussed. So example, we are taking this block for the convolution, and when we are multiplying the 3 channels, the 3 channels value with the 3 channels of the filter, then we will get one value. That will be the output in the feature map. But this is the output we get when we have considered only one filter. Now we are interested to consider more than one filter. Maybe this time we are taking 5 filters. At that time we are having 5 feature maps. This is first feature map, second feature map, third feature map, 4 and 5 feature map. Now we will discuss what is the computational cost of the normal convolution. See here, filter parameters, first number of the filter parameters we are taking. Each filter, because we have considered a 3 by 3 size, and each filter is having 3 channels. So filter parameters 27, and the filter positions. The filter positions, it can be 4 by 4. How many number of positions we are keeping the filter? 4 by 4. And it can be also written by using the output. The output becomes the filter position, and number of filters we are using 5. So totally for the computational cost we are getting 2160. Now we will calculate the same thing for the depthwise separable convolution. What is this depthwise separable convolution? We will observe. In the normal convolution we are only considering a filter. The filter, whenever we are taking example, this image is having, this input is having 6 by 6 size, and number of channels if we are considering 3. If the number of channels are 3, then in the filter also, whatever may be the size, whether it is 3 by 3 or 2 by 2, the number of channels must be equal to the number of channels at the input. This is how we are performing the normal convolution. In the depthwise separable convolution, we are taking 2 operations. One is depthwise and pointwise. What is this depthwise and pointwise? We will discuss. Here in the depthwise convolution, example, if the input is 6 by 6 by 3, means the number of channels are 3, then we will consider the number of filters equal to 3. If in the input there are 5 number of channels, then we will consider 5 filters. If in the input there are 10 channels, then we will consider 10 filters. So previously, if there are number of channels equal to 3, then we use it to consider the number of channels of the filter also 3. but now we are not considering the number of channels of the filter. Whatever may be the number of channel, that many number of filters we are considering. If the number of channels are NC, then we are considering the NC number of the filter. Because here the filters are 3, we will finally get a 4x4 matrix feature map. Now the question, because we have used 3 filter, we will get 3 such feature maps. Now the question is how the convolution is happening. The convolution, the first filter, for the convolution of the first channel, we use the first filter. For the convolution of the second channel, we use the second filter. For the convolution of the third channel, we use the third filter. This is how we are performing the depthwise convolution. Now we will discuss how it is happening. See here. We have considered the one filter here. This filter after the convolution of this with this R channel, example, red channel, finally we got 4x4x3, 4x4 output feature map size, and we are getting 3 such filters. This is one 3 such feature maps. This is first feature map. Now we are performing the same operation for the another 2 filters. We will get now 2 other feature maps. What is the computational cost? Now we will calculate. The filter parameters are only 3 into 3 because no channels are there, and filter positions 4x4, and the number of filter 3. So total computational cost is 432. Another step is there. We have completed the depthwise. 432 is a very small number, but also we have to calculate the computational cost due to the pointwise convolution also. Depthwise separable convolution means we are performing depthwise convolution and followed by pointwise convolution. What is this pointwise convolution? We are using a 1x1 convolution or network in network convolution. 1x1 convolution means we are giving the input as 4x4x3 and we are using 5 such filters. So output is 4x4x5. As we already discussed in the previous lectures, the pointwise for the pointwise convolution, I am taking the input 4x4x3 as input and the filter 1x1x3, and the output is 4x4. We are using this block for the convolution operation. We are multiplying the 3 values of this filter block with the corresponding 3 values of the channels, and then we will add, that will become the first value in the feature map. Similarly, we perform the same operation for the next values of the feature map also. Like that, we got this feature map with size 4x4. Now we are using 5 such filters. Feature map size is 1x1, and we are using 5 such filters. And the number of channels in this, feature map, the filter size is 1x1. Filter size is 1x1, and we are using 5 such filters. And each filter is having 3 channels. Because we are using 5 filters, now in the output feature map, the size of the output feature map is 4x4, and we are having 5 such feature maps, so it is output size is 4x4x5. Now if we calculate the computational cost due to pointwise convolution, it is 3. The filter parameters, because 1 into 1 into 3, filter position 16, and number of filters 5, 80, and it is 240. So cost of the normal convolution is 2160, whereas the cost of the depthwise separable convolution, when we are taking the depthwise convolution, the cost is 432. When we take the pointwise convolution, the cost is 240. So total cost is 672. The cost of the depthwise separable convolution is 672. The cost of the normal convolution is 2160. The ratio is 0.31. Means compared to normal convolution, the depthwise convolution, depthwise separable convolution, which we are using here, it is giving very less cost. So computationally, it is very efficient. So in the paper, they mentioned, the paper that was published in 2017, they mentioned the formula also 1 by NC prime by plus 1 by F square, where NC prime is nothing but the filter size, and F is nothing but, NC prime is nothing but number of filters we are using, where F is nothing but the filter size. So if we use the number of filters 5, then it is 1 by 5 plus 1 by 9. But in practical case, we use the 512 filters. So 1 by 512 plus 1 by 3 square. 1 by 3 square, it is all 1 by 512 plus 1 by 3 square. So it is almost 10 times cheaper than the normal convolution. If we have the input 3 channels, then we are considering the 3 filters. Because we have considered the 3 filters, output feature map also we are getting 3. But we can even increase the number of the channels. This time we are having 6 channels. So we expect 6 filters to be there. So output also 6 feature maps are there. Output is correct, 6 feature maps are there. But the filter number here, it looks, we have considered only 3 filters, but this is the conventional representation for the depthwise convolution. Even though the number of filters are more than 3, the number of filters may be 5 or 6 or 10 or 20 or 512, we always represent this black. Means whenever we are representing 3 filter black like this, it represents we are applying the depthwise convolution. Same thing is applicable for the pointwise convolution also. When we are representing these 3 blocks, it does not mean only we are using 3 filters. It is the this representation is saying that we are using the pointwise convolution. Now we are discussing about the architecture of the MobileNet. We are considering the MobileNet V1. This is the block we have discussed as depthwise separable convolution. First, we are performing the depthwise convolution and followed by the pointwise convolution. In the MobileNet V1 architecture, this same block will be repeated 13 times. After that, it will be flattened. So pooling layer and then fully connected layer. And after that, softmax. Means this block will be repeated 13 times. After that, they are using pooling layer. After that, flattening and then fully connected layer and then softmax. Whereas in MobileNet V2 architecture, a residual connection is observed and expansion block is added. Means the same one by one convolution. Here we are using for the expansion. Here we are using the 1 by 1 convolution for the compression or shrinking, you can say. We are calling this as a projection. So this layer is called as in the MobileNet V2 bottleneck module, bottleneck block. This block is called as bottleneck block. This block will be used 17 times. After that, pooling layer and then fully connected layer and then softmax layer. So MobileNet V1 and MobileNet V2 architecture difference is here we are in the MobileNet V2 we are using the skip connection, whereas in the MobileNet V1 we are using only the depthwise convolution and the point convolution. Now we are discussing about the MobileNet V2 bottleneck block. As the depthwise convolution and pointwise convolution of MobileNet V1 discussed. That's why we are now discussing MobileNet V2 bottleneck block. We are taking the input block maybe n by n by 3. And after that, we are using a pointwise convolution, means 1 by 1 by 3. Because we are having 3 channels, we are taking the filter, in the filter also we are considering 3 channels. So it is 1 by 1 by 3. And we are taking 18 such filters. Now it is expanded n by 18. Now we are performing the depthwise convolution. While performing the depthwise convolution, as we discussed already, when the number of channels are 18, we should consider the number of filters also 18. So 18 filters we are taking. We are using the same padding. So at the output, we will get same size as the input n by n. And the number of channels also 18 because we are using 18 filters. After that, we are using a pointwise convolution. This time we are using the pointwise convolution 18 with 1 by 1 with 18 channels because the input is having 18 channels. So this filter is also having 18 channels. We are considering 3 such filters. So output is n by 3. you can observe the shrinking in the output here. You can observe the expansion of the output here. So that's why this black is called as expansion black, and this black is called as projection black. So this is expansion layer. You can think this is the projection layer. Both here in the both the cases we are using the point convolution only, pointwise convolution only. In between we are using the depthwise convolution. The advantage with this approach is here we are giving the chance to calculate computationally. It is giving more rich way to calculate the parameters. But in the later stage, we don't want it to be carried forward to the next stage, because when we want to use in a devices like mobile, we should have a very less number of channels. So that's why we are shrinking again to n by n by 3 and we are forwarding it. So this structure gives a very good way, especially for the memory, the devices which are having less memory like mobile CPU, we can use this MobileNet V2. This is the paper in 2019 that was published about the MobileNet V2, inverted residuals and linear bottlenecks. This was the title. So here in the MobileNet V1, as we discussed, only depthwise convolution and pointwise convolution, these two blocks were used, whereas in the bottleneck block of the MobileNet V2, we are using the expansion and the depthwise convolution. And pointwise convolution, we are using two times. One time we are using for expansion and second time we are using for the projection. We are using a skip connection here. So this bottleneck block is repeated for 17 times. After that, pooling and fully connected layer, and finally softmax layer. This is the structure of MobileNet V2.